not to be confused with memorization. Tabling redirects here. For the parliamentary procedure, see table. In computing, memoization is an optimization technique used primarily to speed up computer programs by storing the results of expensive function calls and returning the cached result where the same inputs occur again. Memoization has also been used in other contexts, such as in simple mutually recursive descent parsing in a general top-down parsing algorithm that accommodates ambiguity in left recursion in polynomial time and space. Although related to caching, memoization refers to a specific case of this optimization, distinguishing it from forms of caching such as buffering or page replacement. In the context of some logic programming languages, memoization is also known as tabling. See also lookup table. Etymology. The term memoization was coined by Donald Michie in 1968 and is derived from the Latin word memorandum, usually truncated as memo in the English language, and thus carries the meaning of turning the results of a function into something to be remembered, while memoization might be confused with memorization. Memoization has a specialized meaning in computing. Overview. A memoized function remembers the results corresponding to some set of specific inputs. Subsequent calls with remembered inputs return the remembered result rather than recalculating it, thus eliminating the primary cost of a call with given parameters from all but the first call made to the function with those parameters. The set of remembered associations may be a fixed size set controlled by a replacement algorithm or a fixed set, depending on the nature of the function and its use. A function can only be memoized if it is referentially transparent, that is, only if calling the function has exactly the same effect as replacing that function call with its return value. While related to lookup tables, since memoization often uses such tables in its implementation, memoization populates its cache of results transparently on the fly, as needed, rather than in advance. Memoization is a way to lower a function's time cost in exchange for space cost, that is, memoized functions become optimized for speed in exchange for a higher use of computer memory space. The time-space cost of algorithms has a specific name in computing: computational complexity. All functions have a computational complexity in time and in space. Although a time-space trade-off occurs, this differs from some other optimizations that involve time-space trade-off, such as strength reduction, in that memoization is a runtime rather than compile-time optimization. Moreover, strength reduction potentially replaces a costly operation, such as multiplication, with a less costly operation, such as addition, and the results in savings can be highly machine-dependent, non-portable across machines, whereas memoization is a more machine-independent, cross-platform strategy. Consider the following pseudocode function to calculate the factorial of n. Function factorial: if n is 0 then return 1, by the convention that 0 equals 1, else return factorial times n. Recursively invoke factorial with the parameter 1 less than n, and if end function for every integer n such that n0. The final result of the function factorial is invariant. If invoked as x equals factorial, the result is such that x will always be assigned the value 6. A non-memoized version of the above, given the nature of the recursive algorithm involved, would require n+1 invocations of factorial to arrive at a result, and each of these invocations, in turn, has an associated cost in the time it takes the function to return the value computed. Depending on the machine, this cost might be the sum of the cost to set up the functional call stack frame, the cost to compare n to 0, the cost to subtract 1 from n, the cost to set up to the recursive call stack frame, the cost to multiply the result of the recursive call to factorial by n. the cost to store the return result so that it may be used by the calling context. In a non-memoized implementation, every top-level call to factorial includes the cumulative cost of steps 2 through 6 proportional to the initial value of n. A memoized version of the factorial function follows. Function factorial: if n is 0 then return 1, by the convention that 0 equals 1, else if n is in lookup table then return lookup table value for n, else let x equals factorial times n. Recursively invoke factorial with a parameter 1 less than n. Store x in lookup table in the nth slot. Remember the result of n. For later, return x. End if end function. In this particular example, if factorial is first invoked with 5, and then invoked later with any value less than or equal to 5, those return values will also have been memoized. If it is then called with a number greater than 5, such as 7, only 2 recursive calls will be made, and the value for 5 will have been stored from the previous call. In this way, memoization allows a function to become more time efficient the more often it is called, thus resulting in eventual overall speed up. Some other considerations. Functional programming. Memoization is heavily used in compilers for functional programming languages, which often use call-by-name evaluation strategy to avoid overhead with calculating argument values. Compilers for these languages heavily use auxiliary functions called thunks to compute the argument values, and memoize these functions to avoid repeated calculations. Automatic memoization. While memoization may be added to functions internally and explicitly by a computer programmer in much the same way the above memoized version of factorial is implemented, referentially transparent functions may also be automatically memoized externally. The techniques employed by Peter Norvig have application not only in Common Lisp but in various other programming languages. Applications of automatic memoization have also been formally explored in the study of term rewriting in artificial intelligence. In programming languages where functions are first-class objects, automatic memoization can be implemented by replacing a function with its calculated value once a value has been calculated for a given set of parameters. The function that does this value for function object replacement can generically wrap any referentially transparent function. Consider the following pseudocode. Function memoized call: if f has no attached array values then allocate an associative array called values, attach values to f, and if f.values arguments is empty then f.values arguments equals f, and if return f.values arguments end function. In order to call an automatically memoized version of factorial using the above strategy, rather than calling factorial directly, code invokes memoized call. Each such call first checks to see if a holder array has been allocated to store results, and if not, attaches that array. If no entry exists at the position values arguments, a real call is made to factorial with the supplied arguments. Finally, the entry in the array at the key position is returned to the caller. The above strategy requires explicit wrapping at each call to a function that is to be memoized. In those languages that allow closures, memoization can be effected implicitly by a func-to-factory that returns a wrapped memoized function object. In pseudocode, this can be expressed as follows. Function construct memoized func to allocate a function object called memoized version. Let memoized version be if self has no attached array values. Then, self is a reference to this object. Allocate an associative array called values. Attach values to self, and if self.values arguments is empty then self.values arguments equals f, and if return self.values arguments, and let return memoized version end function rather than call factorial. A new function object memfact is created as follows. memfact equals construct memoized functor. The above example assumes that the function factorial has already been defined before the call to construct memoized functor is made. From this point forward, memfact is called whenever the factorial of n is desired. In languages such as Lua, more sophisticated techniques exist which allow a function to be replaced by a new function with the same name, which would permit factorial equals construct memoized functor. Essentially, such techniques involve attaching the original function object to the created functor and forwarding calls to the original function being memoized via an alias when a call to the actual function is required, as illustrated below. Function construct memoized functor allocate a function object called memoized version. Let memoized version be if self has no attached array values. Then, self is a reference to this object. Allocate an associative array called values. Attach values to self. Allocate a new function object called alias. Attach alias to self. For later ability to invoke f indirectly, self.alias equals f, and if self.values arguments is empty, then self.values arguments equals self.alias, not a direct call to f, and if return self.values arguments, and let return memoized version end function. Parse is when a top-down parser tries to parse an ambiguous input with respect to an ambiguous context-free grammar. It may need an exponential number of steps to try all alternatives of the CFG in order to produce all possible parse trees. This eventually would require exponential memory space. Memoization was explored as a parsing strategy in 1991 by Norvig, who demonstrated that an algorithm similar to the use of dynamic programming and state sets in Early's algorithm, and tables in the CYK algorithm of Koch, Younger and Kasami, could be generated by introducing automatic memoization to a simple backtracking recursive descent parser to solve the problem of exponential time complexity. The basic idea in Norvig's approach is that when a parser is applied to the input, the result is stored in a memo table for subsequent reuse if the same parser is ever reapplied to the same input. Richard Frost also used memoization to reduce the exponential time complexity of parser combinators, which can be viewed as purely functional top-down backtracking parsing technique. He showed that basic memoized parser combinators can be used as building blocks to construct complex parsers as executable specifications of CFGs. It was again explored in the context of parsing in 1995 by Johnson and Dora. In 2002, it was examined in considerable depth by Ford in the form called pack-rat parsing. In 2007, Frost, Hafiz and Callahan described a top-down parsing algorithm that uses memoization for refraining redundant computations to accommodate any form of ambiguous CFG in polynomial time for left recursive grammars and theta for non-left recursive grammars. Their top-down parsing algorithm also requires polynomial space for potentially exponential ambiguous parse trees by compact representation, and local ambiguities grouping. Their compact representation is comparable with Tomita's compact representation of bottom-up parsing. Their use of memoization is not only limited to retrieving the previously computed results when a parser is applied to a same input position repeatedly, it is specialized to perform the following additional tasks. The memoization process accommodates an ever-growing direct left recursive parse by imposing depth restrictions with respect to input length and current input position. The algorithm's memo table lookup procedure also determines the reusability of a saved result by comparing the saved result's computational context with the parser's current context. This contextual comparison is the key to accommodate indirect left recursion. When performing a successful lookup in a memo table, instead of returning the complete result set, the process only returns the references of the actual result and eventually speeds up the overall computation. During updating the memo table, the memoization process groups the ambiguous results and ensures the polynomial space requirement. Frost, Hafiz and Callahan also described the implementation of the algorithm in PADL-08 as a set of higher-order functions in Haskell, which enables the construction of directly executable specifications of CFGs as language processors. The importance of their polynomial algorithm's power to accommodate any form of ambiguous CFG with top-down parsing is vital with respect to the syntax and semantics analysis during natural language processing. The Xziger site has more about the algorithm and implementation details. While Norvig increased the power of the parser through memoization, the augmented parser was still as time complex his earliest algorithm, which demonstrates a case of the use of memoization for something other than speed optimization. Johnson and Dora demonstrate another such non-speed related application of memoization. The use of memoization to delay linguistic constraint resolution to a point in a parse where sufficient information has been accumulated to resolve those constraints. By contrast, in the speed optimization application of memoization, Ford demonstrated that memoization could guarantee that parsing expression grammars could parse in linear time even those languages that resulted in worst-case backtracking behavior. Consider the following grammar. S, an XBXBXX, X, reads. An S is either an A followed by a C or a B followed by a D. The production XX, X, reads. An X is an X followed by an optional X. This grammar generates one of the following three variations of string. XAC, XBC, or XBD. Next, consider how this grammar, used as a parse specification, might affect a top-down, left-right parse of the string XXXXXXBD. The rule A will recognize XXXXXB, and then return to S, and fail to recognize AC. The next clause of S will then descend into B, which in turn again descends into X and recognizes the X's by means of many recursive calls to X, and then AB, and returns to S and finally recognizes AD. The key concept here is inherent in the phrase again descends into X. The process of looking forward, failing, backing up, and then retrying the next alternative is known in parsing as backtracking, and it is primarily backtracking that presents opportunities for memoization in parsing. Consider a function rule accepts semi-input, where the parameters are as follows. Rule is the name of the rule under consideration. Position is the offset currently under consideration in the input. Input is the input under consideration. Let the return value of the function rule accepts semi-input be the length of the input accepted by rule, or 0 if that rule does not accept any input at that offset in the string. In a backtracking scenario with such memoization, the parsing process is as follows. When the rule A descends into X at offset 0, it memoizes the length 5 against that position and the rule X. After having failed at D, B then, rather than descending again into X, queries the position 0 against rule X in the memoization engine, and is returned a length of 5, thus saving having to actually descend again into X, and carries on as if it had descended into X as many times as before. In the above example, one or many descents into X may occur, allowing for strings such as XXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXXX S must recursively descend into X as many times as there are X's. B will never have to descend into X at all, since the return value of rule except semi-input will be 16. Those parsers that make use of syntactic predicates are also able to memoize the results of predicate parsers as well, thereby reducing such constructions as some rule to wander sent into A. If a parser builds a parse tree during a parse, it must memoize not only the length of the input that matches at some offset against a given rule, but also must store the subtree that is generated by that rule at that offset in the input, since subsequent calls to the rule by the parser will not actually descend and rebuild that tree. For the same reason, memoized parser algorithms that generate calls to external code when a rule matches must use some scheme to ensure that such rules are invoked in a predictable order, since for any given backtracking or syntactic predicate-capable parser not every grammar will need backtracking or predicate checks. The overhead of storing each rule's parse results against every offset in the input may actually slow down a parser. This effect can be mitigated by explicit selection of those rules the parser will memoize.